A packaged unit can look complete on a vendor drawing and still arrive on site fundamentally unfit for integration. That is the uncomfortable truth. The pump may run. The compressor may meet its rated capacity. The control panel may energize. The skid may even pass the factory acceptance test. Yet the package can still fail as an engineered system because the specification did not define interfaces, utilities, transportation limits, maintainability, safety obligations, documentation, construction responsibilities, or performance guarantees with enough precision. When you prepare a packaged unit specification, you are not merely purchasing equipment, you are defining a compact process plant that must operate safely inside a much larger facility. Your specification must therefore answer one decisive question. Has every technical, physical, operational, and contractual boundary been made visible before the purchase order is placed? If the answer is no, the missing details will not disappear. They will return later as vendor deviations, interface clashes, site modifications, commissioning delays, commercial claims, and operating restrictions. The purpose of a packaged unit prompt list is simple. Force the engineering team to identify every critical requirement before ambiguity becomes expensive. Start with the package environment. Where will the unit operate? Is it onshore or offshore? Which country, city, industrial zone, or climatic region? Will it face salt-laden air, high humidity, desert dust, monsoon rain, freezing temperatures, seismic forces, or marine exposure? Environmental protection cannot be treated as a generic note. It determines enclosure ratings, corrosion protection, material selection, winterization, ventilation, electrical classification, and equipment life. Then establish the hierarchy of requirements. Your specification must make it clear that when statutory, international, national, local, and project requirements conflict, the more stringent requirement applies unless formally resolved. This prevents a supplier from selecting the easiest interpretation while the project assumes the safest one. Define every special process operating, safety, environmental, and quality requirement. State whether the package must undergo HAZID, HAZOP, control HAZOP, constructability review, maintainability review, or other assurance activities. Do not assume that a vendor understands which reviews are mandatory or who must participate. Next, define the package boundaries. Where exactly does vendor responsibility stop? At the skid edge, at mating flanges, at junction boxes, at terminal strips, at the local control panel, at the battery limit isolation valve? Each discipline must define its own interface points. Process, piping, mechanical, structural, instrumentation, electrical, civil, control systems, and construction cannot rely on one vague statement such as complete package. Complete means different things to different people. A vendor may consider the package complete without mating flanges, hookup spools, field cables, earthing conductors, lighting, insulation, commissioning consumables, or integration logic. Your project team may assume all of these are included. That difference becomes a variation order. Layout requirements must also be explicit. State plot limitations, equipment spacing, access routes, escape paths, maintenance clearances, valve accessibility, instrument visibility, and possible future expansion. A tightly packed skid may reduce vendor fabrication cost, but create decades of operating difficulty. Designed for the technician who must remove a motor, calibrate a transmitter, pull a heat exchanger bundle, or operate a manual valve during an emergency. If the equipment cannot be safely reached, the package is not well designed. Transportation is another engineering condition, not merely a logistics activity. Specify maximum dimensions, weights, lifting methods, transport frames, shipping protection, dynamic acceleration forces, and route restrictions. Define whether the unit will be shipped as one module or split into transportable sections. The package must survive lifting, road transport, sea fastening, unloading, and reassembly without distortion or loss of alignment. A skid designed only for operating loads may fail under transportation loads. Noise and vibration limits must be quantified. Low vibration and acceptable noise are not engineering requirements. State allowable values, measurement locations, operating conditions, and acceptance methods. Identify free issue items that the project will provide. Define responsibility for receipt, inspection, storage, installation, testing, and warranty integration. Free issue equipment creates a dangerous contractual gap when neither party clearly owns its performance inside the final package. List spare parts, commissioning spares, startup spares, operating spares, and special tools. A proprietary coupling tool or calibration device discovered after handover can immobilize otherwise healthy equipment. The scope of supply must identify every major component. It should also establish the supplier's fundamental responsibilities. The supplier must comply with the complete specification, use suitable design practices, workmanship and materials, and provide motors, instruments, and other standardized items from approved manufacturers where project standardization requires it. Material selection cannot be delegated casually. The supplier must select materials compatible with the process fluids, temperatures, pressures, and environmental conditions. Any uncertainty must be escalated to the appropriate materials specialist. Hazardous materials must be declared. Prohibited substances, including asbestos-containing materials, must be explicitly excluded. Most importantly, define the performance guarantee. What must the package achieve? Capacity, pressure, temperature, efficiency, power consumption, emissions, noise, vibration, turndown, availability, product quality, or some combination of these. At which operating points will the guarantee apply? Normal operation, rated operation, minimum flow, maximum ambient temperature, fouled conditions, startup. A guarantee without defined conditions is not a guarantee. It is a future argument. The supplier must also identify conflicts between codes, standards, and project requirements, rather than silently selecting one. Technical conflicts must be raised for resolution before fabrication, not documented later as a justification for non-compliance. Now consider erection and site installation. Will the supplier erect the package, supervise erection, or provide installation instructions only? State applicable site labor agreements, contractual site conditions, and restrictions. Where site assembly is required, define match marking, flange alignment, bolt tensioning requirements, earthing continuity across flange joints, and reassembly procedures. For offshore and seismic applications, weight and center of gravity are critical design inputs. Require a weight control procedure, regular weight reports, and defined maximum acceleration loads. An inaccurate center of gravity can compromise lifting design, module integration, and structural safety. Use modularization and maximum pre-assembly where it reduces field work, but do not maximize pre-assembly blindly. The final module must remain transportable, liftable, inspectable, and installable. Define responsibility for pre-commissioning and commissioning at site. Flushing, drying, leak testing, loop checking, motor solo runs, logic verification, performance testing, and operator training must not fall into an undefined space between contractor and supplier. Site utilities require the same discipline. Provide the supplier with available utility conditions: pressure, temperature, flow, voltage, frequency, quality, composition, and reliability. Include water analysis, meteorological data, and relevant design basis information. Do not tell the supplier that instrument air is available. State its minimum pressure, maximum temperature, dew point, quality, and design availability. Do not say cooling water available. Define supply and return conditions, allowable pressure drop, chemistry and fouling assumptions. Specify winterization, steam tracing, electrical heat tracing, freeze protection, and cold start requirements. Consult construction and contracts teams for site-specific restrictions that design engineers may not see. Also state that the supplier must provide any temporary utilities needed for construction, testing, or pre-commissioning, unless the project explicitly agrees to provide them. The process definition begins with P&IDs and associated documents. Attach representative P&IDs, legends, line lists, valve schedules, process flow diagrams, heat and material balances, and package limit drawings where applicable. Define numbering conventions for equipment, instruments, piping, and valves. Some projects require suppliers to avoid assigning final tag and line numbers until project review. In that case, the supplier must still show equipment type, service, line size, and specification, so the project can allocate numbers during document review. Do not permit the numbering process to become an excuse for incomplete drawings. The package P&ID must show process limits, isolation points, drains, vents, relief devices, control loops, shutdown functions, utility connections, and interfaces. Overpressure protection must be addressed explicitly. Who sizes the relief valves? Who validates relieving scenarios? Where does the discharge go? Is the package protected against blocked outlet, control valve failure, external fire, thermal expansion, utility failure, and other credible cases? Low temperature protection must also be defined where depressurization, flashing, refrigeration, or cold ambient conditions can push materials below their allowable temperature. Piping requirements must identify applicable codes, standards, and design contingencies. Include project requirements for piping design, materials, valves, and fittings unless approved supplier standards are accepted. Mandatory layout rules must cover personnel access, operating clearances, maintenance envelopes, escape routes, and the visibility and accessibility of valves and instruments. Define utility connections individually. Decide whether each utility will enter the package through a single common connection or multiple service-specific connections. Specify mating flanges, blind flanges, flange ratings, facing, materials, gaskets, and bolting. Identify prohibited or non-standard pipe sizes. Small deviations in pipe size philosophy can create unnecessary field reducers, special components, and stocking problems. Nozzle load limits must be stated. The supplier must know the loads that connected equipment can tolerate, while the project piping team must know the allowable forces and moments at package interfaces. Also define cutting allowances for hookup spools, overall dimensions, weight limits, and any piping materials required for field assembly. Clarify whether the supplier provides fabricated spools, loose components, or both. Structural requirements begin with the governing codes and load cases. Specify dead loads, operating loads, maintenance loads, lifting loads, transportation loads, wind, seismic effects, vibration, and accidental loads where relevant. If weight control or structural certification is required, say so. Define standards for structural steel, platforms, ladders, handrails, and access systems. When a skid is required, it must be suitable not only for supporting equipment, but also for lifting, transportation, and anchoring to the foundation. Large components supplied separately may still require supplier-designed platforms, ladders, and handrails. Do not assume these will be completed automatically by another discipline. Tell the supplier how the package will be supported. Concrete foundation, gravel pad, piles, steelwork, or another system. Where piles or structural beams are involved, define their number, spacing, and interface constraints. Even protective packing must be considered. If part of the skid receives different preservation or shipping protection from the rest of the equipment, the supplier must identify it. Mechanical requirements must state the applicable equipment codes, standards, and design contingencies for vessels, heat exchangers, pumps, compressors, turbines, and other machinery. Project-specific specifications should be issued where necessary. When supplier standards are accepted, the acceptance must be deliberate rather than accidental. Even nameplates need definition. Decide whether supplier standard nameplates are acceptable subject to approval or whether project and customer formats are mandatory. Nameplates affect asset identification, inspection, maintenance, and regulatory compliance throughout the equipment lifecycle. Instrumentation requirements are often where package integration succeeds or fails. Issue the applicable instrument cable, material, installation, automation, control, fire and gas, and testing requirements. Include the approved supplier list, cause and effect diagrams, and any project-specific packaged unit instrumentation philosophy. Provide blank or partially completed data sheets for vendor completion. Do not allow instrument details to remain buried inside proprietary drawings. Define signal types, communication protocols, segregation, termination philosophy, junction box requirements, intrinsic safety barriers, hazardous area certification, shutdown architecture, alarm philosophy, and interface with the plant control system. The supplier must understand whether control is local, remote, or shared. They must know which logic resides in the package controller and which functions reside in the main plant system. A package that operates perfectly in isolation can fail during integration because permissives, trips, alarm priorities, fail-safe states, and communication ownership were never defined. Electrical requirements need the same clarity. List governing codes, project electrical specifications, motor specifications, and motor data sheets. Define hazardous area classification and the required protection concepts for all electrical equipment. Specify earthing philosophy, lighting scope, and the extent of supplier-provided earthing materials. Decide whether the package will be fully pre-wired to package junction boxes or wired at site. Full pre-wiring may reduce field labor, but only when cable routing, segregation, termination, and maintainability are properly engineered. Provide voltage levels, frequency, system fault levels where applicable, and the intended use of each supply. Define control voltage, heater supply, lighting supply, and emergency power requirements. Avoid duplicating specifications, because duplicated requirements frequently conflict. Where the package deviates from a general project specification, state the variation explicitly. Include electrical heat tracing and cable requirements where applicable. Painting and corrosion protection must be aligned with fabrication, shipping, and site completion. State whether the supplier delivers the package fully painted or whether final painting will be completed at site. Define surface preparation, primers, intermediate coats, finish coats, dry film thickness, environmental exposure class, and touch-up procedures. Specify galvanizing where required. Different surfaces may require different treatments. Exposed steel, insulated surfaces, hidden areas, high-temperature surfaces, and non-ferrous components cannot all be handled identically. Define color coding for piping and systems where the project requires it. Thermal insulation must identify whether its purpose is heat conservation, cold conservation, condensation control, freeze protection, or personnel protection. When insulation is essential to the process performance guarantee, the supplier should remain responsible for its design and installation. Otherwise, the vendor may guarantee performance, assuming insulation that another contractor installs incorrectly. For fired equipment, include refractory requirements. Where insulation is supplied loose for site installation, identify each item and require detailed installation instructions, material schedules, and fastening details. Acoustic insulation follows the same principle. State maximum allowable noise levels, operating conditions, measurement locations, and whether acoustic enclosures, barriers, silencers, or lagging are required. Metallurgical and welding requirements must address corrosive, erosive, and low-temperature services. Specify any requirements beyond the minimum code provisions. Impact testing, heat treatment, normalizing, stress relief, material traceability, positive material identification, hardness control, weld mapping, special consumables, or additional non-destructive examination. These requirements must be included before procurement and fabrication. Retrospective material verification is slower, more expensive, and less reliable. Finally, quality assurance must not be reduced to a generic sentence saying the supplier shall have an approved quality system. Define the project QA requirements in full. Identify inspection levels, hold points, witness points, document review points, inspection and test plans, material certificates, welding records, calibration certificates, test procedures, non-conformance controls, factory acceptance testing, preservation checks, final release documentation, and manufacturing record books. Quality cannot be inspected into a package at the end. It must be designed into the procurement process from the beginning. This is the central lesson. A packaged unit specification is not a collection of discipline notes. It is an integration contract. Every unclear interface transfers risk to site. Every undefined test transfers risk to commissioning. Every vague guarantee transfers risk to operations. Every omitted maintenance clearance transfers risk to the technician. Every unverified utility condition transfers risk to performance. Every unassigned responsibility becomes a future claim. When you lead a packaged unit procurement, do not ask only whether the vendor has included the main equipment. Ask whether the package can be transported, lifted, installed, connected, powered, controlled, protected, operated, maintained, tested, and expanded without engineering improvisation. That is the real definition of a complete package. The strongest specifications do not become stronger by becoming longer. They become stronger by removing ambiguity. Your objective is not to describe every bolt. Your objective is to ensure that every critical decision has an owner. Every interface has a boundary, every performance claim has a test, and every foreseeable risk has been converted into a clear requirement. Do that before inquiry, and the package becomes manageable. Ignore it, and the project will engineer the missing specification at the most expensive possible location, the construction site. File site, turn, file, 0.